Okay, I'm going to talk about a more complicated rotation example. And really what's going on here is there's a rotation plus a scaling. And so the transformation looks a little more awkward. So let me just think about this example integral. If it's the integral over r of an ellipse function, 3x squared minus 5xy plus 3y squared, where your region R is bounded by the ellipse 3x squared minus 5xy plus 3y squared equals 2. And in these kinds of problems, they're actually going to give you the transformation to use. So using x equals square root of 2u minus the square root of 2 over 11v, y equals square root of 2u plus square root of 2 over 11v. The reason they're going to give this to you is because deriving this is kind of a mess, and it requires a little bit of linear algebra, so I think it's beyond this course. Really, the point of this is this ellipse is lopsided, right? A good ellipse would point either toward the x-axis or it would point toward the y-axis. But this doesn't either. Not that I'm going to attempt to draw this out, but that's really the point, what's going on here. So you need to rotate to a better form where it's pointing along one of the main axes. And then you need to also rescale if you want to integrate this so that it becomes just a unit circle, or any circle. So that's really what's encapsulated by this complicated transformation. Really what's going on is there's a rotation plus a rescaling. So if you're wondering where that comes from, that's really the idea of what's at play here. So you can expect, I mean, this is kind of all you can do because all we know how to do is integrate over circles. We don't know how to do any ellipses. So you would hope that's what you should get when you plug the transformation in. So you can expect the UV equation to be a circle. So that is, if you plug in UV or x, y into the ellipse equation. So let's just do that. I would say the first step is to plug in x, y. So our ellipse equation, 3x squared minus 5xy plus 3y squared equals 2. Now we're going to plug in those square roots. So what we'll get is 3 square root of 2u minus square root of 2 11ths v squared. And I'm going to put the y squared and the x squared next to each other. It'll turn out there's some cancellation that happens. Squared. And then finally you have this minus 5. And then you just plug in each argument. Remembering there's a plus and there's a minus. It's actually very crucial there's a plus and a minus because these will help cancellations. So now if you expand, you get 3 square each term. I'll write the squares first. So 2u squared plus 2 11ths v squared. And now we have the cross terms, which I'm going to put in red because they will actually be 0. So minus 2 times 2 over square root 11 uv and then plus something very similar. You can tell it's just going to be different by a minus sign, right? So the squares will be the same. And then now we'll have a plus. 2 times 2 over square root of 11 uv. You can see the red terms cancel. Okay, now let's look at the minus 5 term. So minus 5, now it's a difference of squares. So, it's just a plus b, a minus b. That should be a squared minus b squared. So you should get 2u squared minus 2 11ths v squared. Okay? So if you just simplify this a little bit, this should give you, let me just put all the u squareds in one place. So 6, that's the first term, and then it's plus 6, that's the second term, and then minus, what is this, 10? That's the third term. Now let me add the v squareds. Let's see, we have a 6 11ths for the first term. Then we have a 6 11ths for the second term. When you're doing bookkeeping like this, I like to just mark a term that I've considered so I don't double count. And then finally, plus a 10 11ths for that last term. So this should give you 2u squared plus, what is this? That's 12, that's plus 10 over 11, so that's 22 over 11. Well, would you look at that? We got a 2v squared. If that were any other number than 2, I would have gotten scared because that would not be a circle. As it is, now our equation is 2u squared plus 2v squared equals 2. Well, would you look at that? We get u squared plus v squared equals 1. So whoever wrote this problem knew what they were doing, and they gave you the good circle. Circle of radius 1. So you can see that the substitution worked, and the next step is just to calculate the Jacobian. I would call this our region R bar, which was transformed from our bad region R. So let me just delete this. So now the next step is to calculate the Jacobian. So xy divided by uv, remember this is xu, I'm using partial derivatives, remember xu equals the partial derivative of x with respect to u, and so on for the others. Yv, these are the good terms. Now you just switch the variables, that'll give you the off diagonals. So our transformation was x equals square root of 2u minus square root of 2 over 11v, y equals square root of 2u plus square root of 2 11v. So now we just take the coefficients now, because these would be our partial derivatives. So xu is square root of 2, xv is negative square root of 2 over 11ths, yu is square root of 2, yv is square root of 2 over 11ths. Take the determinant, this is 2 divided by square root of 11 plus, remember there's a minus sign, really this is a minus minus, plus this 2 over square root of 11, so we get 4 over square root of 11. And so this term, what it counts for is the compression of the it counts for the compression of the rescaling. I guess this is an expansion. Okay, so now we can do our integral. So our integral over r of 3x squared minus 5xy plus 3y squared. I think that's what it was. Yes. dA, really our dx dy. Now if we transform, this is now an integral over r bar. Remember, this was the ellipse. This is now the circle of, well, see, here's the thing. This is exactly the same as the edge of the ellipse, right? And we actually show this thing is equal to u squared plus v squared. So this is u squared plus v squared. That's why they actually put this there. If this were anything else, you would get something messy. But now we have this nice u squared plus v squared times the Jacobian, which is 4 over square root of 11, and then times our du dv. And remember, our r is just the unit circle, so you can now solve these using polar coordinates. U equals r cosine theta, v equals r sine theta. And this becomes quite straightforward because this, of course, is just r squared. Okay, so you'll end up with something like what? R cubed dr d theta, and that's very easy. Okay, so I hope this trick was useful. Thank you for watching.